In this lab, we're going to identify the three different laws of motion set out by Newton in like the late 1600s. These three laws of motion basically dictate how everything works in the universe, how things move and stop moving, and it gives us a great idea of how forces work and how we describe them, not only with observations but also mathematically. So the first law of motion is that an object at rest tends to stay at rest, and an object in motion tends to stay in motion unless there's some unbalanced force that, does something about that. In other words, things don't move for no reason. Okay, I have two bottles here. As long as I don't do anything to them, they're just going to stay still. There is a force acting on them right now. That's the force of gravity pulling them downwards, but I'm providing a force in the opposite direction to keep them from moving in that direction. So they're staying still. They're kind of in a point of balance. The forces that are acting on them cancel each other out, so no motion happens. Now, if I want them to move, all I have to do is have an unbalanced force take effect. So for example, if I remove my hand from under this ball right here, this racket ball, okay, the force of gravity will win out and take over and cause the ball to start moving. Okay, that force is what causes the ball to move. Okay, now I could also have the force of gravity take effect on this guy here, but I don't want to damage my floor. Okay, this has quite a bit more mass to it. All right, now they're about the same size, but they're not the same mass, not even close. Just by looking at it, you can probably tell by a good guess, this is probably metal. Okay, and most metal things you've dealt with, you probably have realized, are dense. They have a lot of matter packed into some amount of space compared to other materials. Okay, you've also probably dealt with things that are dense or that have a lot of mass and tell that they take a lot of kind of oomph to get moving, right? Or if they are moving, it's kind of like you have to put in a lot of oomph to get them to not move. Okay, so just comparing these two, it's a lot easier to get this racket ball to move than it is to get this giant, basically, ball bearing to move, this giant steel ball to move. Okay, not only that, but when I need to stop this racket ball from moving, it's really easy compared to this, which is kind of tough. Like if I threw this up much higher, I'm gonna start hurting my hand. All right, so we have a name for this. It's called inertia. Basically, it's the idea that stuff that has a bigger mass is harder to change its motion, whether you are getting it to start moving or getting it to stop moving or something in between, speeding it up or slowing it down. So the first law of motion says that things don't move for no reason. And if you are going to try and get something to move, it depends on how much stuff is there, how much mass you have that you're trying to move. All right. If someone said, hey, stop that marble, it's rolling down the hallway, you probably wouldn't think twice about stopping it with your foot. But if someone said, hey, stop that bowling ball, you'd probably be like, no, I'm going to let that one roll past. Because the bowling ball has a lot more inertia. It's going to take a lot more force to stop its motion. And it would probably take a lot more force to get it moving at that speed compared to something as small as a marble. Okay? The second law of motion says that when things speed up or slow down, that is because of a force. Okay? Based on what we heard from the first law of motion, when things are in motion, they tend to stay in motion unless there's a reason for them not to. Okay? Like this ball, when it's rolling, when a ball is in motion, it rolls and rolls and rolls, and eventually it will stop. Okay? Now that's due to a force, okay? And that force is slowing its motion down. And in order to get it moving that fast, I need to apply a force to speed it up. Okay? But as long as the force isn't acting on it, it should move at the same speed. So anytime something is moving at a different speed, it's changing its speed, it's speeding up or it's slowing down, there's a force involved. Okay? We have a fancy science word for when things speed up or slow down. We call that acceleration. So when something with mass is speeding up or slowing down, it's accelerating. Even something as simple as throwing something up and down in the air demonstrates this. Okay? There's a force of gravity that is pulling this downwards after I apply a force upwards to this ball or to this ball. Okay, now when that mass is moving fast as I throw it up in the air, okay, and it's changing its speed to go from not moving to moving, okay, it's accelerating. But as I have a force acting downwards on it to constantly pull it back down towards the center of the earth, that's gravity, well, that's going to slow it down. You'll notice it doesn't continue at this speed and just goes up and up and up forever. Okay? Eventually, it has to stop its motion and come back down. Okay? It stops somewhere up here just for a moment, and then it starts to come back down this way. And the farther it falls, the faster it goes. You'll notice right after the peak of where it falls, it's moving pretty slowly compared to how fast it's moving down here by my hand. Okay, if I were to stop it up here, it doesn't have as much of an effect as if I let it come all the way back down to my hand. Let's watch that again. Versus, ooh. Okay? So, acceleration is when something is speeding up or slowing down in either direction. Okay, and that has to happen because of a force. If something is not being acted on by an unbalanced force, in other words, something's not pushing or pulling out of that balance, out of that equilibrium of things not moving or something like that, then they should continue their motion or non-motion as they are. But if something is in motion or something is not moving, then they stay in that motion or non-motion without some force acting upon it. Okay? Now, this brings us to the third law of motion, because most of the time we don't see things continue their motion at a constant speed. Like, just from experience, you'll know that if I take this stack of playing cards right here, and I push them across the table, they're not just going to keep going and going and going across the table and then across the other side of the room. They stop. And part of that is because I ran into a quarter. Move this sticky note out of the way. The other thing is friction. Not super exciting, but it's something that we are used to in this daily life, that things have friction. When things rub together, okay, there's a force involved there. Okay, so I apply a force to accelerate these cards to get them moving faster and faster, to stop, or to get them moving from a place of rest. So they're not moving. I apply force so they move, and not only that, they start moving faster and faster, but then they also slow down and eventually stop because of the force of friction. Okay? The force of friction is called a reactionary force. It happens as a result of some other force. All right? We don't really talk about friction when something is not moving. You know, like, oh yeah, there's friction. Well, maybe, not really. We really only talk about friction when something is in motion, rubbing against something. Okay? It's that kind of resistance force against something's motion. Same thing goes with air resistance, and something's moving through the air. Okay? It doesn't just continue forever at some constant rate. It kind of slows down a little bit in its path and eventually drops a little early because of all the air that it's running into and it's slowing down. Okay? It's kind of like another kind of friction. Okay? Now, every force has some kind of force that acts in opposite to it and an equal amount. All right? Like the force that my hand is putting out on this ball to oppose the force of gravity. If the force coming from my hand was greater than the force of gravity, then I'd be moving the ball upwards. And if the force of gravity was greater than what I'm doing with my hands, then I would be moving the ball downwards. Okay? But as long as they are balanced, nothing changes. Okay? Sometimes that equal and opposite force will be the only thing there that will keep stuff from, not moving at all. Okay? Or it will be there to get something to stop moving or get something to start moving. All right? So sometimes it's hard to kind of notice. It's also sometimes kind of hard to notice with inertia because some things are so big, you'd never notice that, there's an equal and opposite force. Okay? Like, for example, let's set this here for a second. When I throw this racquetball, like this way, it's going to have an equal and opposite force pushing back on me. Okay? So if I toss the racquetball forward like that, I have a force that's pushing the ball this way. The ball is actually pushing back on me this way. But I'm so big compared to the ball, I would never notice. It's the reason why we're allowed to walk. Okay? The laws of physics basically say that as we are walking, we're basically pushing on the earth, and the earth is pushing back. It happens to be that the earth is so much bigger than us that it's way better at pushing us than we are at pushing it. So technically, when you walk and when you jump, you are pushing back on the earth, and you're causing it to move. It's just so slight of a motion that you would never even notice. Okay? We probably wouldn't even be able to detect how small of a motion that is. But on the other hand, you are so much smaller in comparison to the earth that you have an easy time moving around. okay? As my foot pushes down on the earth, I move in the opposite direction, okay? And the earth is doing that by pushing me back, okay? You can do this kind of and kind of prove yourself to it with larger objects that are more relevant to your mass. So if you go and find a friend and then put your hands on each other and push on each other, you'll have a force that pushes you backwards, okay? If you don't, put your foot down to brace yourself or something, you put your feet together, do a little patty cake and then push, okay? You're gonna be going backwards a little bit, okay? You can do this with a wall too, but a wall is not going to move much because it's so much bigger and heavier than you are. Again, kind of like the earth, you're never even gonna notice that it's moving even a slight amount, okay? So, those are our 3 laws of motion. In short, objects don't move unless there's a force acting upon them, and they don't stop moving unless there's a force acting upon them. 2, when something speeds up or slows down, that's because of a force, okay? And that speeding up or slowing down process is called acceleration. And 3rd, every force comes in a pair, okay? There's some equal and opposite force acting on it. So if something is being forced in some direction or another, that's because there's a force somewhere in there that is winning out over another force. Okay, or there's an imbalance in your inertia. You have something that's way bigger or way smaller, and so you'd never even notice the motion of the other thing. Okay, so we're going to be looking for those 3 laws of motion in this lab with 6 little short activities. Okay, the first activity we're going to do is what I call coin hockey. What I've got here is a stack of 5 quarters lined up here, and I've also got a penny here. In comparison, this stack of 5 quarters has a lot more mass than this penny here. Okay, now what I'm going to do is I'm going to slide this penny at this stack of quarters and see if I can knock the bottom quarter out without letting this stack tumble over and fall. Okay, so this is actually a little bit harder than you might think because you got to have some good aim and you make sure you don't, fling the penny off to the side. But I'm lucky in that I get to cut out the footage where I miss it, whereas if you're doing it in the lab, your friends get to watch you miss it a whole bunch of times unless you have really good aim. So, here we go. Hey! I got it on first try. That's pretty lucky. Okay. Let's see if I can do it a second time. Hey! There we go. Okay. So you'll notice the stack of quarters doesn't really move anywhere, but I'm able to knock these quarters out from underneath it. Okay. So one law of motion that we're showing here is the first law of motion. We're able to move these individual quarters, okay, without moving this whole stack. Okay, the inertia of this whole stack is keeping it in rest, okay? It's keeping it from moving, and it's not going to move unless we have a significant force acting upon it. And the more mass there is, the harder it is to get it to move. You've probably seen this with a magic trick or with a party trick where someone pulls a sheet out from underneath something and everything stays in its place, okay? Those objects at rest tend to stay at rest unless they have a significant force acting upon them. So if you have a very nice light sheet that you're able to pull out straight from underneath them without causing a force lifting them up or pulling them down or something like that, you can just pull it right out from underneath it, okay? Now we also have a good example of Newton's third law with some reactionary forces. You'll notice that when this penny collides with a quarter, they kind of go in opposite directions of each other. You have the penny go one way and the quarter goes another way. They kind of collide and split that direction. So whether you hit the quarter straight on or at an angle, you'll notice that they kind of move in opposing directions. Oops. So my penny kind of hit at an angle and moved off to the right, where the quarter moved off to the left. Let's try this again. Okay, same kind of thing. This time the penny moved left and the quarter moved right. Let's give it one more try. Okay, this time the quarter moved this way, the penny moved that way. Okay, so they kind of move in opposing directions from opposing force. When the penny hits the quarter, it has a force going this way, and there's an equal and opposite force moving the penny this way. Okay, so that's coin hockey. Next is going to be coin the cup, or coin in a beaker in this case. Okay, I'm just going to take a playing card, like this King Hearts, place it here. All right, and put a penny on top of it. All right, and again, this is kind of like the magic trick where you pull the sheet out from underneath a bunch of glass, wine glasses or cups or plates or something like that, and they don't move, but the sheet does, okay? So instead of pulling this out, I'm gonna flick it because I can apply my force with a much quicker impulse than trying to pull it out like this. So I'll just flick this, and the penny, instead of going with the card, should just fall straight down. Oops. Now, if I can flick it well. Oh my gosh. There we go. Let's do this another time with, this time we got the ace of clubs. Let's do a couple quarters this time. Go. Yeah, there we go. Let's do a big stack just to see. Queen of diamonds, oh, that's kind of curved. Let's do king of spades. All right. Oops. There we go. That was a good flick. Okay, so when I apply a force to the card, it moves. Here, let's do this one because it's got a curved edge. It moves like that. Okay. It goes from rest to moving faster and faster and then eventually slower and slower. So it accelerates when I hit it with that force. Okay. Something doesn't change its speed or change its motion without a force acting upon it. So that's Newton's second law, that the speeding up or slowing down, the acceleration that happens, is directly resulting from the force that's acting upon that object that has mass. Okay? And we also have, again, a good example of the first law of motion, that things at rest tend to stay at rest unless they're acted upon by a force. Now, since the card is what I'm acting on the force with, and the coins are just kind of there for the show, they don't have a whole lot of force acting directly upon them. Now, if I flicked the stack of quarters or the penny on top of this, then it would definitely move too. But if I'm not providing a whole lot of force with the card on the stuff on top of it, it will just go along with it while the stuff at rest stays at rest and then falls down into the cup. Now, of course, it falls because of gravity, and so there's a force here that causes the motion of the coins. It's going downwards rather than going outwards. So it's another kind of sign of, an object at rest tends to stay at rest until there's something acting upon it. Gravity pulls the coins down when there's nothing to stop them, with an equal and opposite force going the other direction. So you'll start to see that a lot of different laws of motion tie together with each other. We don't really find them independently very often, but it kind of depends on which part of the motion you're looking at. That's how we kind of identify these different forces. Activity 3 is with these spring scales. Okay, we use these in the lab to measure force. Okay, so on this spring scale, you have this N here that stands for newtons. That's our unit of force. And you've got a hook down here that you can attach things to or pull from. Okay, and as that pulls down, that shows more and more newtons of force that it takes to move the spring on the inside. Okay, so these spring scales are used to measure force. Okay, now I can hook two spring scales together, like so. Like this, and pull them apart from each other, like that. Let me turn this so I've got the force side aiming outwards on both of these. Let's see if I can kind of get them back far enough so you can see. There we go. So I'm going to pull on both of them pretty equally. All right, and they kind of go pretty equal length. Or I could pull the left one more, or I could pull the right one more. Okay, notice how that force is kind of shared. Okay, so even if I'm trying to keep this hand still and I'm trying to just pull this one, if I'm trying to keep this hand still, I'm just pulling this one. Okay, they both end up moving, which is kind of interesting. Okay? Now they don't move, and they don't speed up or slow down unless I'm acting upon them with a force. And if I stop putting that force on there, then they stop speeding up or slowing down. Now there's a force inside the spring, so that when I pull on this, and when I stop applying my force, okay, they accelerate in the opposite direction to pull themselves back together. Okay, so I'm applying a force, and the spring's applying a force. Force, 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 like that. Okay. We've also got an equal and kind of opposite force acting here, so you can kind of try and figure out which of the three laws of motion best applies to that scenario. So that's activity 3, the spring scales. This is another example of an activity where I get to cut out all the parts that don't work, and then you guys have to do it in lab in front of your friends, and it's not as easy as it looks. What we're going to do is an old trick where you place a coin on your elbow, and you put your hand up by your ear or by your neck, on your shoulder, and you try and catch this with the hand that you have back here. Okay? Now again, sometimes it's harder than it looks, but we're going to use some laws of motion to help us out with this, to make this possible. Okay? And you have to act quickly before the coin accelerates too much to fall out of your reach. But you also have to have some good reflexes so you don't just swat the coin out of the way. That's most of the time what I end up doing, is I just swat the coin and it goes flying across the room. Okay? So let's see if I can do this. Ah! First try. Okay? So, well, I guess I can say it's the first try, but you'd never know if I cut it out. So, again, you place a coin on your elbow and you have your hand up by your ear or by your shoulder on your neck. Okay? And we want to let the coin drop by lowering our elbow. And even though I'm going to turn my elbow like this, okay, that force on my elbow is not necessarily going to carry to the coin. It's just staying here. So the only force that's going to be acting on it is going to be gravity pulling it downwards, okay, where my hand is going to swoop in and try and grab the coin before it can fall too far and can accelerate to go too fast. Okay, let's see if I can do it again. Ah! You can also do this with a stack of coins. So let's do that. Let's try and up it since I got 2 in a row. So I'm going to do it with a stack of 5 quarters. All right. Now I'm going to psych myself out. Oh, okay, I got 1 of the quarters and I flung the rest of them everywhere. Okay. And you can find all kinds of videos, Guinness World Records of people doing this with so many coins, it's ridiculous. But it's just another fun little party trick that uses the laws of motion to explain this. So kind of like the coin falling in the cup, we have the first law of motion on our hands that's kind of helping us out with this, with inertia, where we have objects at rest that tend to stay at rest unless acted upon by force like gravity. So until I give them a reason to move, they're not going to move. Okay? And they have to accelerate, okay? So that force of gravity is going to cause them to fall downwards, which means they move faster and faster, but they're starting with no motion. So they're going to be moving faster and faster from that starting point of not moving, which means I have a chance to catch them before they start moving too fast to escape my grasp. I'll try one more time with the stack, just so I can embarrass myself again. I think part of it is thinking too hard about it, so I'm going to try not to... Okay, I got 2 quarters, and I kind of got 3, and then I dropped the 3rd one. Which is better, but I'm not winning any world records here. Okay. If the party trick activities were not like your thing, and you had a hard time getting to catch the quarter, or do that kind of stuff, this one might be for you. So we have a balloon with a penny inside of it. Here. Kind of rattling around in there, okay? And what we're going to do is we're going to swirl the balloon like this to get the penny to move inside it, okay? And sometimes it's easier if you have it upside down like this first and hold it kind of from the bottom this way, okay? But we're going to swirl it to get the penny to start moving inside it. We want to get it moving fast enough that the penny is going to kind of climb the sides of the balloon. So it's going to have motion, and it's going to want to stay in motion until the friction eventually stops it. So if I start to move it around, okay, eventually it will stop rolling and sliding around in there because friction will slow it down. But otherwise, it's going to keep moving as much as it can. Rolling objects tend to have a very less amount of friction. They don't experience as much friction as something that's sliding. So if we can get the coin to roll, it's going to stay in motion for a lot longer, and it's going to have less friction stopping it or slowing it down, accelerating it in the opposite direction. Okay, so that's what we're going to try and do. We're trying to get the penny to roll along the inside like a wheel. Okay, so I'm going to try it like this first. I'm going to spin it like this. You can kind of hear that noise. Okay, so you've got the penny pushing on the balloon. You've also got the balloon pushing back on the penny. And even once I stop moving the balloon, the penny keeps going around and around and around. Now, this might be kind of hard to see on the video, but thankfully this is something you can easily do at home or, you know, on some simple materials. But I'm going to still try and get it closer a little bit. So. Hopefully you're able to see the penny kind of going around and around in a line like this. And you can try getting it to go in a couple different directions, so you can have it going horizontal. That one's going for a while. Kind of fun to watch. You've probably seen something similar to this in like shopping malls, where you have kind of those like coin vortex things, where it's like a big bowl and you drop a coin and it goes around, and then it finally drops in. Okay, so we have the force of the penny rolling along the side, and you also have the bowl, or in this case the balloon, kind of pushing back. Okay, so that way the penny doesn't just go off in the distance or something like that. Keeps its motion consistent. Okay, so we have kind of the third law of motion helping us all, and also the first law of motion saying that as long as the penny is going, it's gonna stay in motion until the friction or until gravity finally wins out and stops it from moving. Okay, you might also have seen people do this in like circus acts or something, or in stunt acts where you have a motorcycle in a big spherical cage and they go around and around and around and they're going sideways, okay? Or you might have seen cars that go up the side of a ramp in an action movie or something like that, and they stay moving forward, but they're like driving sideways off, you know, the perceivable ground. Okay, this is much for the same reasons. Okay, Newton's laws are in action that cause this. You have an equal and opposite force of the surface pushing back. So, you know, the car or the penny or the bike or whatever can kind of stay and continue its motion along that path. Okay, here's our last activity, and it's the spinning tires activity. The last two, I guess, are kind of spinning themed. So the last one is spinning penny, activity 5, and this is spinning tires, activity 6. So we're going to use one of these tumble buggies here, which you can turn on to get its tires moving. So its tires are moving around like this. Now, when the tires hit that surface, basically what it's doing is they are having a force going this way, right? Okay, they're going this way. So when they hit a surface, and you have that force going back this way, the car doesn't move backwards. Whatever is underneath the tire moves backwards. All right? And a lot of times you'll hear this when we talk about, you know, something like how you walk, where you move forwards because you're pushing the earth backwards and stuff like that. And it's hard to understand it that way because it's so hard to think of the earth moving just from your motion. Like, it almost feels like it's unbelievable. So this demonstration can kind of help with that. So instead of trying to move the whole earth or the surface of a table, we're just going to move a piece of paper, okay, and show how that motion relates to the motion of this buggy. So we're going to have the car turned on already, and then set it down on the paper. See how the paper moves backwards? And the car moves forwards. Okay? Now, when I just kind of set it down on top of it, it's not a lot. Again, it's hard to notice when it's just for that instant. But if I'm holding it down and constantly applying that force, you can see it much more emphasized. Just how much it's pushing that back. Okay? When it's only for a second, it's kind of hard to see. Okay? And it'd be even harder to notice when you have something that's of much larger size, a much larger mass, that has a lot more inertia. Okay? In this case, the laws of motion that I want to kind of emphasize are, you know, the fact that we have stuff moving and accelerating, both the car and the stuff underneath it accelerate. Okay, not just the car, both of these accelerate. And that's because of Newton's third law, because we have a reactionary equal and opposite force. Okay, there's a force causing the car to go forward, and therefore a force causing the paper to go backwards. Okay, or you could say that the force causing the paper to go backwards is the same as the force causing the car to go forwards. Okay, so hopefully this has helped you to kind of get an idea of these three laws of motions and see them in action so you can start to recognize them all over the place.